Hi everyone, in today's video we'll be diving again into the world of USB device development with Raspberry Pi Pico. Specifically, we'll be building a USB device with two CDC ports using the tiny USB library. One port will be used for debug prints and the another will be for data transfer. On top of that, we'll be handling USB device events like mounting, unmounting, suspend and resume. And to make it visual, we will use the onboard LED of Pico. Now let's talk about the TUSBconfig.h file. As we discussed in the previous video, this file is critical for configuring tiny USB. It defines all the macros and control how our USB behaves. If you haven't seen the video yet, make sure to check it out for the full explanation. For our project, the only change we need to make here is to increase the number of CDC class. By default, it's set to 1. We will change it to 2 to support 2 virtual COM port on our Raspberry Pi Pico. That's literally all the modification we need in this file, keeping everything else intact. Next, let's move on to defining USB descriptor in usbdescriptor.c. This is where we tell the host exactly how our USB device is structured. Since we are adding a second CDC interface, we also need additional endpoint definitions. Remember, each endpoint address follows a simple pattern: endpoint address equal to EPNUM, that is the endpoint number, odd with, in or out based on the type. This helps the USB stack know whether the endpoint is in or out transfer. Also, each CDC interface requires two interfaces, one for control or interrupt and one for data transfer. So for single CDC device, we need two interfaces. Since we now have two CDC devices, we require a total of 4 interfaces. We also need to add interface, endpoints and string descriptor for the new CDC interface. Here, as you can see, we have added the descriptor for CDC1 with string index at 5. This setup ensures host can properly distinguish between both virtual COM ports and route the data correctly for each interface. Now let's dive into the application firmware. Now one of the key features we are implementing is the onboard LED blink pattern to visually indicate the USB state. Here's the mapping of blink interval to the device state. When the device is not mounted, the LED will be blinking in every 250 millisecond. When the device is mounted, in every 1000 millisecond, and when the device is in suspended state, it will blink in every 2500 millisecond. We have also used a variable blink interval millisecond to track the current interval depending on the device state. The actual blinking is handled in the LED blinking task function. It uses a simple timer check based on board millis to toggle the LED state every blink interval underscore millisecond. This ensures the LED blinks accurately according to whether the device is mounted, unmounted or suspended. And controlling the board LED is done via Pico standard library function board LED write, passing true or false for on or off respectively. Continuing with the application firmware, we implement the mount stat callback functions. These callbacks are invoked automatically by tiny USB core whenever the USB device changes state. Here's the breakdown. TUD mount callback is called when device is mounted by the host. TUD unmount callback is called when device is unmounted. TUD suspend mode when the bus is suspended, and TUD resume callback when the bus is resumed. Inside each of these callback, we update the blink LED millisecond variable to change the LED blinking pattern. So the onboard LED always reflects the current device state. This gives us a clear real-time visual indication of what's happening with our USB device. Next, let's handle the data reception and transmission for our dual CDC ports. Tiny USB provides two key features for reading data from CDC interface. TUD CDC receive, it reads bytes from the default CDC interface, which is interface 0, and TUD CDC end receive, it reads byte from any specific CDC interface where ITF is the interface number, 0 for CDC 0, 1 for CDC 1 and so on. Since we have two CDC port, we are using the second function to handle data separately for each interval. Here's the TUD CDC receive callback, which is invoked whenever a CDC interface receives data from the host. Inside the callback, we read the data into a buffer using the TUD CDC end read. If the data comes from CDC 1, we process it, null terminate the string, print it to the console and echo it back to the host using TUD CDC end write and TUD CDC and write flush. This setup allows our Pico to receive data on one virtual COM port and echo it back, effectively demonstrating communication on multiple CDC interfaces. Finally, let's look at the main function that ties everything together. First, we initialize the board on the tiny USB stack using the board init and TUSB init. Then we call stdio init all to let the Pico SDK use the first CDC interface for the standard IO. This enables printing on the console. The main suspend loop is simple but critical. We continuously call TUD tasks to let tiny USB handle USB event and LED blinking tasks to manage the onboard LED according to the current device state. This combination ensures our dual CDC device is always responsive to the host while giving a real-time visual indication of mounting, unmounting and suspend resume state. So here I am demonstrating how the function that we have implemented works. Like first I will showcase how the mounting and unmounting status will be seen from the board LED. I didn't find any way to unmount and mount it and showcase mounting and unmounting procedure. So for the workaround, what I'll do is I will just connect this Raspberry Pi Pico to power supply rather than USB, and we can see the unmount state. So the LED should blink for 250 milliseconds and it should go off and it should again blink. So right now it is not connected to any PC or laptop, it is just connected to a power supply, and you can see the LED blinking for 250 milliseconds and turning off. This showcase that our device is not mounted. Now what I'll do is I'll disconnect the power supply and connect it to the PC. You should hear the connection sound. So it got connected and the device got mounted. You can see the LED blinking for 1 second and going off. So now for the suspend mode, what I'll do is I will disable the driver fully. So let me disable the device. Yes. So I've disabled the device. No. Still it is mounted. But what if I can disconnect it? Let me disconnect it and let me connect it back again. As you can observe, the LED is lighting for like more than 1 second and going off for a longer period of time. That means our device is in a suspend mode. But now what I'll do is I will enable the driver, enable the device and enable the device. Now you can see the LED status change. Now it's blinking every 1 second or 1000 milliseconds. This is showing how we have achieved a mount, unmount and suspend status using the LED. Let's try the next experiment where we will connect to the different COM port. The first one is COM6, which is our CD0. So let's connect it. And let's connect to COM7. I think it's already connected. And for the option, let me go to line mode. It's in line mode. Let's try to send something to the device. So after sending, we should see the data transfer or the data coming from CDC1 in this terminal and the standard IO showcased in, or the printf showing in CDC0 in this terminal, COM6 terminal. So let's see. You can see, right? We received the received data that we are sending from here, from the code, if you can see, and the printf you can see in COM6. Hello world. Yes. So see, it's working. To wrap up, in this project we successfully implemented a dual CDC device on Raspberry Pi Pico using the tiny USB library. One CDC interface is used for standard I/O while the other handles the data transfer. We implemented mount, unmount, suspend and resume events visually indicated by the onboard LED. Host to device communication is handled through the TUD CDC RX receive callback on CDC1 while the CDC0 is used for standard I/O. Finally, we verified the data echo functionality on the host using the terminal program like CoolTerm or PuTTY. This setup gives us a fully functional dual virtual COM port device with real-time USB state monitoring. If you found this video helpful, be sure to hit that like button, subscribe for more content like this, and let me know in the comments your suggestion. Thanks for watching, and I will see you in the next one.